Hello, fans of GeoGebra. We have another insight. Here is a slanted beam. It's pinned at the left edge. It's a roller support on the right edge, which means that it must stay on this horizontal surface, but it can slide along this horizontal surface. The loads are known. One of them is pure east, the other is pure gravity down. And where this hits the beam is also known. We could just put that on a point that slides along this beam. How do we solve this using Muller-Breslau is exactly the same as what we did for trusses, believe it or not. It's a mechanism that has to be reduced down to the minimum. So how does this work here? So we have a loft, and the loft could be as big as you want in the beginning here, and that's a vertical loft because I am seeking the vertical right reaction. So I have a vertical loft here. However, in the earlier chapters of the Muller-Breslau, we just lofted it up here and we stretched that beam and called that good. But now we're not going to do that. We're going to respect the rigidity of this member and find the new position that satisfies the original length of the beam. That's really easy to do here. We just take a circle radius length of the beam and we draw a horizontal line through the lofted point so that the roller slides along this horizontal line. And where the circle and that horizontal line intersect, that's the new right edge of the beam. I drew that as a dotted line. And then it's really nice to see the loft in the east direction. It's just this component, the horizontal movement of where the 1500 was and where it is, and the vertical movement of the 1000 unit force where it was and where it is. And we'll call that loft G, the other one loft E. Notice, however, though, that for increasing my loft E goes to the left, which means that's negative work on the east force. And the loft G goes up, which means that's negative work on the gravity force. Balancing all that out means the reaction times the loft plus the work of the east force plus the work of the gravity force all equals to 0. I bring the east force to the other side. I bring the gravity force to the other side. They become positive then, and then I divide by the loft. If you do understand algebraic statics, you will see that those would both be positive for an upward reaction on the right pin. Theoretical number here is known, and then as we reduce the loft, we see what's happening here, and as you bring it down, obviously it's an asymptotic solution, and the right-hand reaction will hit the theoretical reaction at an infinitely small perturbation. So this is probably the first time that the Muller-Breslau has been really rigorously applied for a general type of load, whether it's vertical or horizontal. This technique will work. If it's purely vertical, you don't have to go through the constraint of not stretching the beam, but I like this as a visual, especially to see the signs. I think it becomes super obvious how the energy is flowing through the system.